fine.
So welcome to the first Fusion EP talk in 2020. And today, Davide Silvagni is with us from Germany. Davide, hi. How is it going in Munich?
Very good, very good.
How is the weather?
No, it's kind of great. It's not so cold. So better than usual.
Great. So we would like to start with a bit informal introduction to know each other better. And I see that you started your bachelor in engineering, and then you joined Fusion EP program, master program in nuclear science and engineering. So it feels like you always wanted to learn fusion. And could you tell us what was your inspiration? What led you to this field?
So I think, I don't know, attracted by the possibility to create, to have fusion energy realized, and I want to be part of this, or want to learn something more about fusion. And that's what drove me into the master. And then things escalated. I like it more and more, and now I'm doing the PhD, and I like it even more. So it's going well.
Great. And in a formal way, how do you describe your work, what you're doing to a relative? Let's say you're at Christmas table and people are asking, okay, Davide, so what are you actually doing at your work? What fusion is and why do we need it?
So, okay.
That's a difficult one.
Yeah, I know. I've started to do it. So, okay, now here I'm doing my research. It's on magnetic confined fusion, which is a way to create energy, like the same energy that is created in the sun, fusion reactions, but on Earth, and using the magnetic fields. So that's why it's called magnetic confined fusion. Because with magnetic fields, you can create a certain sort of a cage that can keep your fuel close to each other and to create fusion reactions. And now the problem is that inside the this fusion cage, we reach very high temperatures, 10 times the temperature of the sun, so actually very, very high. And then this fuel that is at high temperatures at some point escapes this cage and reaches the elements of the reactor where this plasma should go. And these elements have high energy on it. And so basically my PhD is, part of my PhD is to study how this energy goes into these elements and how we can find clever ways with the physics to reduce this energy going into these elements and keep these elements, because then these elements can melt, can crack. If you think about a fusion reactor in a power plant. So the challenge is to find a scenario that can have energy to these elements not so high. Okay.
Yeah, this brings us to the main topic of the talk, which is I mode and whether it's useful for future reactors. So could you again tell us in your own words, what is it and why is it important?
I mode.
Yeah.
Okay. So, I mean, I don't know if maybe in this case some slides will help. I don't know, but anyway, if we want to keep it just easy, so IMOD is a confinement regime that shows an improved energy confinement. So that's why it's called IMOD. The I stands for improved, meaning that usually has a temperature pedestal. So it has a temperature pedestal at the edge of the plasma. And at the same time, it doesn't have a density pedestal. So it has a particle, an ELM-like particle confinement, meaning so you have enough particle confinement. The particle confinement is not so high, while the energy confinement is higher. And this is particularly attractive because it couples the good things of ELM mode and H mode, namely that you can reach high energy into the core with the high temperatures, but you do not have the problem of impurity accumulation, or you have less impurity accumulation because of the enhanced particle confinement. And you have, if you think also about like a burning plasma, you have less helium accumulation and then dilute your fuel. So in principle, this is a very attractive scenario. So that's the main one characteristic. And the second characteristic, which is maybe the most important one, is that this scenario is free of edge localized modes. And now when people are doing and thinking about what could be a possible scenario candidate for a steady state reactor, the more we do research, the more we realize that we cannot accept any edge localized mode in this scenario, because these modes will cause a very strong increase of energy to the divertor targets. And if you have to think about a reactor that lasts 20 years without changing the divertor target each day, or I don't know, each year, you have to avoid these edge localized modes. And so this regime is free of edge localized modes. So that this makes it particularly attractive.
I see, that sounds very good, but what are the disadvantages, may I ask?
So I mean, the thing is that now there is research going on, and there are many, more than disadvantages, there are open questions. So as usual, one has to find a regime that is compatible with the requirement of a DMO-like reactor. And I-mode, so still we need to prove some things which are missing. Maybe the most important is detachment. So the compatibility of I-mode with detachment. This is something that has been, they started to look at it in Alcator mode a few years ago, and they saw difficulties. So detachment is what is detachment? So if you want to avoid strong power loads to the divertor and particle loads to the divertor, the way to do it is to have some. So usually is to create a certain like a pillow of neutrals in front of your divertor. So in a way that you do not have plasma anymore. In this way, the temperatures are much lower in front of the divertor, so you have much less energy, and also you have much less particle erosion. To create this pillow of neutrals in front of the divertor, this is what we call detachment. Usually, you need to puff, so to do impurity seeding. So you puff impurities, which means you put impurity is anything which is different from the fuel. So in this case can be other atoms. And these impurities, we puff some impurities that radiate in the scrape of layer. So mainly in the scrape of layer. And in this way you can cool down your scrape of layer in front of the divertor and activate all these charges change recombination reactions that will then allow to have more neutrals in front of it. So that's what is detachment. This detachment is not always compatible with all the confinement regimes, because if you puff impurities, then the impurity also change. So they enter into your system, and they change also. They can enter in the confined region and affect the performances, the characteristics of your plasma. And so it's not obvious that I-mode and detachment will go together. So going back to the question, in Alcador, they started to study it and they found difficulties. And when they were puffing impurities, they started to see a back transition to L mode. So apparently the puffing of impurities was causing to lose the improved energy confinement at the pedestal. We have done recent experiments also in ASDEX last year, and we will do actually next week. So in the next 2 weeks, there will be a particular campaign in ASDEX where we can study many IMOs. It's 2 very IMO intense weeks there will be. And we also found difficulties for detachment in IMO, but still, I mean, we have ideas to try to improve it and I mean, this is the beginning of the research, of course. So this is one thing that still needs to be proved, for example, and this is an important thing.
I see, that sounds challenging. Would you give us more information about what exactly you are working on right now? What are your recent achievements and plans? I will give you 10 minutes or whatever you need. If you need some slides, let me know, and you're welcome to describe main goals and results of your work.
So, okay. So I tell you briefly what is, let's say, my PhD. First of all, my investigation, and then maybe we can, yeah, okay. So I am mainly working as an experimentalist here, and I am together with another guy in charge of a diagnostics, which is the infrared camera. These diagnostics can measure temperatures on the divertor tiles, and then you can infer from the temperatures heat flux measurements. With this, you can study many things. I have started my PhD, the beginning of my PhD was not meant to be in IMOD. So the first part of my PhD, I mean, I did a more general study on the power decay length on the scrape-off layer, in the scrape-off layer and on the divertor. And this I did it across different confinement regimes, so in L mode, I mode, and H mode. And yes, and this is a part of my work of the PhD, which is done, and it will be hopefully soon out, published. And then in the, let's say, the second half of my PhD, or more, yeah, 2/3 of my PhD, I started to be very into IMOD. Much more, and let's say that my main topic of research now is on some particular events that we observe in IMOD. We are actually in this moment discussing on the nature of this, and like what is this, how to name them, and how to describe them correctly. Anyway, these events are resembling of, so they show, so IMOD can show in some particular conditions some pedestal relaxation events, so some small pedestal relaxation events, and this is something that has been also seen in Alcador mode. There are not so many studies, and hopefully, if everything goes well, I will go, so maybe I will see some people who are connected here in Alcador in April or May to also collaborate with them with this respect. So these events have been first seen in Alcador, and now we basically saw them also in ASDEX upgrade in some particular conditions. So now my research is basically try to understand when are these stuff appearing, and what are the consequences for the divertor. So what are the heat fluxes, the energy going to the divertor, and trying to understand also the physics. I mean, possibly this is, of course, the main goal of everyone, but this is the most difficult one. And so that's basically my overall topic. But let's say that here I am very much open to discuss also with the people about IMOD in general. So because yeah, I realized that I mean it's a confinement regime which is not so known. I mean in the US, so in the East Coast they know it very well, but maybe in Europe is not super known. And I also, like, doing my PhD and focusing on IMOD, let's say learned a lot on it, so I can share this knowledge to you. So let's say that the slides that I have presented were more on general characteristics of the IMOD to answer some general questions, because I mean now I just said a few things.
Thank you very much. I guess now we can move on to discussion, and Davide will give more details, probably using his slides or not, we'll see. So please feel free to ask any kind of questions. There are no easy questions, and we are grateful for all questions.
Go with the first one. First of all, nice to see you again, Davide. It's been a long time. And I'm mostly interested in all referring the detachment. Well, of course, it's kind of a selfish interest, since I work in the pumping after the divertor for demo. So I was thinking, so the I mode is not fully compatible with detachment, or you are having some problems into reaching the detachment, right?
Yes.
Okay. Yeah. Okay. And what kind of gases are you using for the detachment? Like, are you using like nitrogen, argon, or some other more fancier gases?
So thank you for the questions. The gases that we are using here is in ASDEX is nitrogen, and this is because, so usually nitrogen in ASDEX for the ASDEX scrape-off layer is the best scrape-off layer radiator that you can have, because it radiates at the temperature. So it radiates mainly in the scrape-off layer, also a bit into the confined region, but mainly in the scrape-off layer, because of his, let's say, atomic characteristics. This does not mean that nitrogen will be the better impurity for the demo-like reactor or arc reactor, because yeah, the scrape-off layer temperature can be different, and also because, I mean, nitrogen has the problem of ammonia formation.
Yes,
yes, so I mean, we are starting from nitrogen because it's the, let's say, in principle, the easiest way in present days machines. And I think that also Alcator, I should have, I mean, a slide, but it's not really necessary to answer this question. Also, Alcator used nitrogen, if I'm not remembering wrong. Yes.
Okay. And you know what range of pressures are you reaching in the divertor area with the trying to reach this detachment?
Pressure of what? Of the plasma?
Yes, of the gas, or density, or particle density, and temperature of that area. More or less, like order of magnitude, I mean.
In front of the divertor, you mean?
Yeah, so you are puffing nitrogen in the divertor area and try to achieve detachment. And I was wondering whether if it could be an issue of the pressure range that you have there. That's why I'm wondering what kind of pressure range you have in your divertor area.
Okay, so you mean the pressure of the plasma?
Yes.
So I mean, the problem that we are facing now is more about, I think, the compatibility with the IMOD as a confinement regime with some puffing in general. So because as soon we puff nitrogen, I mean, at some point the IMOD doesn't live anymore. So I mean, then as soon as the IMOD goes back to ELM-mode, the ELM-mode detaches, because the ELM-mode will so actually it's difficult to give a number because the I mode phase with half, it has been short, very short. So, and this is also an ongoing analysis. But anyway, yes.
Yeah.
So I don't know
Okay.
if that's an
Yes. So basically, you have the id mode. You start packing, trying to detach, and then instead of detach id mode, it just goes to detach L mode straight, more or less.
It has a back transition to L mode, and then the L mode.
And then detached.
Yes.
Okay. Great. Good.
And also, there is another thing that I didn't say because I didn't want to complicate the story too much. But I mean, in my opinion, one of the reasons behind all this that makes things a bit more different and complicated is the fact that I mode is obtained in a configuration that is called arrow is pointing towards the X point in the normal plasmas. But then, so the point is that if you instead reverse the BT, the direction of the BT, then this drift goes up. I mean, it's not the drift the cause of the, but anyway, you have this different configuration. Many things change when you change the direction of the toroidal magnetic field. You change the drift in the Skripov layer, etc., etc. And this has the consequence, as one main consequence, that the power threshold to enter H mode gets higher, more or less double. This is something.
But your goal is not to access H mode, right?
Yeah, exactly. Yes. Yeah. The thing is that, so the point is that if you are in a normal configuration, so with the arrow down, and you ramp up the power, you don't have I mode. You will, I mean, it has been obtained only once in Alcado in a very particular case that no one understood, but usually is obtained, you will never obtain I mode. So you will pass from L mode to H mode. Okay?
Okay.
Instead, if you reverse this arrow and you have the arrow pointing up, so not in the direction of the X point, the H mode will happen much later in time in terms of power. So you need double of power. So if before you needed 2 megawatt, now you need 4, for example.
Yeah.
And in this power window that you have in addition, you can find the I mode.
Okay.
And so that's basically the thing. And so that's also, and then why is this connected to detachment? Because I mean, all this stuff, so the fact that you have a different direction of the toroidal magnetic field changes the physics in the Skripov layer of the detachment, because you have different drift direction in the Skripov layer, a different drift direction in the Skripov layer change the at the, let's say, symmetry or asymmetry, so the distribution of temperature and density, and this affects a lot the detachment performances. So actually, now I don't want to say something wrong, but my recent understanding is that is also, I think we're starting now to study this more in ASDEX, this reverse configuration, and I think that I mean, my taste is that it is in general more difficult to detach also H mode in general with this
configuration.
Yes, but I mean, these are not. This is more a taste. It's not, let's say, a scientific statement. So take it with a bit of. But so yeah, I think this is a bit to answer your question. These are the difficulties.
Okay. Yeah. All right. Thank you, David.
David, I was wondering if you have a good picture of the different turbulent modes that may be active in the pedestal. For example, some people have claimed that there is, together with the weakly coherent mode, there might be also the geodesic acoustic mode. I was wondering what's a general picture of what's going on in the pedestal.
I mean, your question is in general about what we understand about the weakly coherent mode and how this affects I mode, right? I mean,
yeah,
more or less. Okay. So so now in these slides, unfortunately, I don't have the right plots. But I mean, this is just to so one thing is that the I mode is characterized by this. I mean, just for the others, by this mode, which is present at the very edge, and this is a broadband frequency in the spectrum of for example, density fluctuations or temperature fluctuations that you can measure at the edge. And this, so the thing is that let's say the mystery of I mode is that the I mode is also only just to understand the plasma physics very interesting, because it's a confinement regime where you decouple somehow energy and particle transport. Because I mean, usually in all the other regimes, when the density, I don't know, so increases at the edge, usually also the temperature increases. I mean, you have the transport of energy and particle is usually coupled. And in I mode, this is not the case. I mean, at the edge at least, because you can have a temperature pedestal without a density pedestal. And so this makes also I mode very interesting just for the physics understanding of the let's say of the plasma, talk about physics. So regarding the stuff of the weakly coherent mode, there is a recent work that is that will be presented at EPS this year by Petermans in ASDEX. And so there were previous studies connecting the weakly coherent mode with geodesic acoustic mode, GAM. To be honest, this is not really my cup of tea. So I have not, let's say, a good overview of what has been done in the past on this argument. What I know is instead that, I mean, here there are, this person, Petermans, has some ideas on how to try to obtain this decoupling of energy and particle transport, and so reproduce the weakly coherent mode. And basically this is somehow I mean, a change in the turbulence at the edge, driven by the difference between ion and electrons at the edge. Yes, but this is something that has been not really in depth studied also experimentally. So about the difference between ion and electron temperature at the edge. And yes, this work will be presented. It's something really brand new.
Okay, thank you.
Anyone else? Questions to Davide? A chance to find out more about I mode?
Yeah. Question.
Yes, Francis?
Okay. Hi, David. Yeah, thanks for the talk, Davide. Like, I have like 2 questions. The first question is, does the plasma stay in this I mode? It depends on how much input power that you give. Like, until you keep the input power to a certain level, the plasma will stay in that I mode, or it depends on various other factors.
Okay. So your question is if with a certain power the plasma stays in I mode, or how we access I mode. Could you clarify a bit more, or I didn't understand?
Yeah. So once the plasma reaches the I mode, so what happens after then? Like what are the parameters needs to be kept so that the plasma stays in I mode, or like what happens? Because you said there's a detachment happening because the heat from the plasma reaches the divertor, so we need this detachment. So, but why this deconfinement is happening when the plasma is in the I mode? So why?
Okay. Yes, exactly. So I mean, this is an example that to show like a typical I mode that you can get in ASDEX, but also, I mean, in Alcador, numbers will be different. But So you see, like before, there is in the top panel the power. So this is the ECRH power, which is stepped up. In the second panel, you see the density, the line average density, with two lines, one line which is passing through the core, one line passing through the edge. You can see that it is constant, more or less, through the entire discharge. Then, in the third panel, you see the pedestal top electron pressure evolution, and in the lower panel, you see the energy of the plasma. And so you can see that a typical I-mode transition, so you can recognize it in this way. You have you are at constant power, so you have the same input power. So at 2 seconds, you increase the ECRH power. And then you see that in the third panel, the electron temperature starts to rise. And this is normal. It's because we are still in ELM mode. It's because we are putting more power, and then the electron temperature, we are heating the electron temperature goes up. But then also, always with the same constant power, at some point, the plasma undertakes a transition. You can see it with this line, dashed line. The electron temperature rises without changing the power. So it's an improvement in confinement, because we are keeping the power constant. And this is due to the formation of the pedestal at the edge. And at the same time, also the energy of the plasma.
So this is to like LH transition, like where we have this transport barrier. So
Exactly. With the only difference that now we are doing a transition to I mode.
Okay.
And then, I mean, if we now didn't change in this discharge, if we stayed with we could stay constantly and stationary in I mode. So now H discharge is performing a different way, but to slightly different stuff. But if you, now even in this discharge, it was staying in I mode all the time, so it's stable in this condition. So we can keep, we have many discharges where we can keep constant and stationary I modes for the entire time. The difficulty comes when you want to puff impurities, for example, or I don't know, when you go to also to high densities in Aztecs is a bit more difficult to get I modes. Actually, yes. So depending on the general, let's say, characteristic of the plasma. This is to show you an important characteristic, in my opinion, of the I mode. So this plot on the y-axis has, let's say, has the power that is crossing the separatrix. And this power basically is the heating power, okay, minus the radiation. And this is the parameter that you use to do your scaling laws for the power threshold. Because one important parameter, operational parameter that you need to know to scale your confinement regime is the power that you need to obtain it. Simply for a matter of design a reactor. People in Alcador know very well. They are designing a new reactor, and then you need to know the power that you need to have to obtain certain confinement regimes. So it's a very important parameter. And this plot is showing actually what I said a bit before. So here you have the power crossing the separatrix on the y-axis, normalized with the density and surface of the plasma.
Davide, can I break in here for a moment? On your slide, you say that CMOD did not achieve H mode at 8 Tesla. That's actually not correct. We did routinely run 8 Tesla H modes in our final campaign.
Really?
Yes, we did. Well, it's high 7 Tesla, but yes.
Ah, okay. Then I have to share this information. I didn't know. Okay, thanks. So forget about this sentence. Yes. So what I was saying is that when the magnetic, so On the y-axis, you have this quantity, which is basically is the power crossing the separatrix normalized to these two, to the density and to the surface, because the power threshold of anything, so of the H mode, but also of I mode, depends on these two quantities. I mean, this is something which is more or less documented with different exponents, but it depends on these two quantities. So that's why it's normalized to that. And on the x-axis, you have the toroidal magnetic field. And you can see that and then you have two lines. The the green line is the scaling of the power threshold from L to I mode. And it has a weak dependence on the magnetic field. You see, so this B to the 0.26. So this, instead, the red line, if I'm not wrong, should be the PLH, so the power threshold to enter H mode, which instead depends more strongly on the magnetic field. So basically, what happens is that if you are at high magnetic fields, the operational window of I mode increases. And so this is to answer your question that if you have, if you then have your reactor with high magnetic fields, then it's much easier to obtain I mode in general, because you have a much higher power, much larger power window, and you have much less problem of, I don't know, stability of the plasma, and I don't know, because if you have 0.2 megawatt more, it jumps into H mode. And that's why in Alcator mode they did a lot of research in I mode, because they really had a wide power window. As you can see in this plot, these plots are only all data from Alcator, and you can see, I mean, how large is the operational window. And in ASDEX we are at 2.5 Tesla, and you can see that it's very small. And in fact, the power window of I mode in ASDEX is actually small. It was a challenge back to, I don't know, 2015 or even before 13 to find stable I mode. Now it's much more easier because we know the tricks.
Okay. Yeah. So I have like one more question on slide 12. So here we have this intermittent burst in the turbulence amplitude, right? So you're basically measuring the density fluctuations, and you're having this fluctuation amplitude being higher at some intervals. So can you tell me what could be the reason for this thing?
So this is a feature that we are observing in most of the I modes that we have here as this upgrade. And so these are measurements of the Doppler effectrometer. The Doppler effectrometer is a diagnostics that can measure the density fluctuation. So can measure many things. You can also somehow measure the density fluctuations, but the main characteristic is that it can measure a different K numbers. So it can really, let's say, diagnose different structures of the turbulence. So the K number is somehow the size of your eddy. I don't know if you, have some turbulence stuff, work on turbulence. Anyway, and here you can see that if you have the turbulence amplitude that you measure with the Doppler simply in L mode, it is, you have a background level which is quite high, and then that's it. I mean, it's what you see in the picture. But then, and this is characterized by this probability distribution function that you can see on the right, which is more or less Gaussian, if you see. Instead, in I mode, the situation is a bit different. You have a reduction of the so you have reduction of background turbulence somehow in the density. So you have, in general, the signal is lower, but then you have sometimes these intermittent spikes, so-called bursts. And this is something that, yeah, it has been studied in us. We are also studying this now and addressing it. And it's, let's say, I don't know if it's a, I don't know if it's a general characteristic of all the I-modes ever in the world. This I would not dare to say this, but for sure is something that we often observe in ASDEX.
Yeah, okay. Yeah, thanks.
So now if there's any more questions to Davide, you're very welcome.
Oh, hey, Davide. Nice presentation. So I'm not really familiar at all with I-mode, so these questions might be very basic, but I hope you can answer them. Do you know if there's been sort of measurements about the plasma rotation during I-mode, and to see if it's at all related to, because H-mode has this like rotation shear, and that's sort of the explanation for the pedestal. Yes. So yeah. Do you know of anything? Yeah, so unfortunately I don't have the plot, but yes, there are. I mean, I'm aware of those in ASDEX. I think, I'm not sure about Alcador, there should be, but anyway, at ASDEX there are for sure. And it has been shown that the radioelectric field, so which is somehow related to the rotation, is so when you have the transition from, so in H mode the radioelectric field has a deep well, okay, and so you have a strong shear at the edge, while in ELM mode this well is less deep, and so then you have a lower or smaller shear at the edge. And I-mode is actually in the middle. So you see that when the plasma is doing the transition and is evolving from ELM mode to I-mode, the ER, let's say, well, is going down until when you have the transition to H mode. So when you have the transition to H mode, the ER well is very low, and this is, and then the D cross B shear is enough to cause the formation of the H mode. So with this respect, it's something in the middle, let's say. Do you think, or do you know if any sort of run like a gyrokinetic simulation on the I-mode pedestal area?
Yeah, so again, I'm more biased because I know the stuff of ASDEX. I guess there should be also something in Alcador. I mean, if also guys connecting Alcador want to add something, please. I know about, in ASDEX there is one person, a PhD, Karl Stimmel, who did some gyrokinetic simulation recently, and actually the paper got published, I think, in this week, so it should be
very recent then.
Yeah. And so on the ASDEX side, these were the first one.
Okay.
And I think at least, and he did some also non-linear gyrokinetic simulations.
Okay, then I'll keep up with that then. It'd be interesting to see what is happening there.
Yes.
If your question, Aaron, was about pedestal gyrokinetics on CMOD, I don't think we have much, but Ann White did some work on gyro on core turbulence in I-mode, and I am doing C-gyro simulations.
Okay.
Oh yeah, and the group in Texas, in Austin, has been doing gyrokinetics also in the pedestal. So they might be the people that on the CMOD side have done more analysis closer to the pedestal.
Yeah, well, like, I mean, with the H mode pedestal, it's still kind of, I don't know, iffy whether or not gyrokinetics, the way it's formulated, is fully applicable. But in the I mode, where you have less density pedestal, it might still be applicable, and it might be interesting to see what the results are. So if you guys are working on it, that's good.
Okay, last chance to ask more questions.
Yeah, I have a
Maybe
question.
You already answered the question.
Hi,
Or I just didn't get it. I don't know. So in this shot, what I noticed here, you have at first the jump of the ECRH power of the heating. Yes. And then you see a very rapid change in the pedestal top temperature and the energy. And this, during the first phase, it stays pretty constant. And then you have another jump at about 2 seconds. And then the pedestal top temperature is kind of constantly rising. I don't know if this is really a thing. But as you said, the transition from L to I mode is not happening immediately after this jump, but after like half a second or something. Mm-hmm. And I mean, the thing what I noticed, or I don't know, maybe it's a very from a very naive point of view, one can maybe think that the transition to I mode happens a little bit more smoothly in this case, because so what I'm referring to is this small increase, or this very slow increase of the temperature and energy there, which is not quite as present in the first ECRH heating phase, but in the second one. And do you know a bit more about this shot, what's going on maybe there in the second phase, why it is constantly rising, the temperature during the second phase and not in the first one? Or yeah.
You mean the second phase? You mean after the dashed line?
No, I mean before the first phase. I mean between 1.5 seconds to about, and the second phase before the dashed line, right? So during the first phase, the electron temperature and the energy is pretty much constant, and after the second phase, there is a slow rise, and after some time,
you mean at 2 seconds?
Appears. Yeah, after 2 seconds. Mm-hmm. It increases a bit, or it increases constantly, and after some time, like 0.3 seconds, then we reach the dashed line, and then we have to transition. And my question is, why is it constantly rising between 2.0 and 2.4 seconds, but it is pretty much constant during the first stage?
Okay.
Sorry for this long question.
This is a question of a guy with an eagle eye. I mean, yes. So I mean, correct. I mean, in principle, so you are right. So I would also, so in general, you would have expected that, okay, you have the temperature constant, and then yes. So, but this actually, I think, so in my opinion, it's, so I mean, this is at least my opinion, the Li transition is never, at least rarely, something like abrupt, that you really see after 1, millisecond, a super strong change. It's always somehow a slow transition. And so that's why it also is kind of a bit difficult to define, because I mean, you see, as you pointed out, between 2.2 and 2.5 seconds, your temperature is rising. So when does it start, this transition? How do you define then what is an I mode and what is an L mode? I mean, it's a bit of a philosophical question. So let's say you have to see this dashed line in this context as a rough way to separate what you have at 2.8 seconds and what you have at 2.1, 2.2 seconds. And what you have in the middle is the transition. So you have your pedestal top temperature, which is increasing kind of stepwise. Usually there is this, you have this sawtooth crashes, and the temperature, instead of going back to the same value, stay a bit higher, and this way you have somehow a stepwise increase of the temperature. I mean, if you, now it's not really visible here, but this you see barely, but you have this stepwise increase. So the reason, the answer is because the transition usually is not like sharp, that you Yes.
Unlike H, put us power.
Sorry.
It's unlike H mode then. When you put us in a certain power and buff it.
Yeah, in H mode it's much more clear, because you have immediately the rise in density. I mean, you have a sharp rise in density and temperature, I mean, simultaneously, and this is very easy to see. Also the DR, I mean, you have many things that change at the same time. So that is very easy to define. With I mode is a bit more tricky.
So that's kind of not the reason, but this also goes like what you said, that it does not immediately jump to I mode, because this is what one would expect if we just know H mode, that this is what one would expect as soon as you put more power, like at 2.0 seconds, it would jump to I mode, but it does not, as you said. Okay, so it's a bit more smeared out, if you want. So it takes a longer time, and it is a continuous process to say. Okay.
Yes.
Thank you. Yes. Okay.
Anyone else would like to ask some questions? Well, last chance. If not, then I would like to thank you again for an interesting discussion. And this talk will be available on YouTube soon. And next talk will be on magnetic perturbations versus turbulence by Francis in a couple of weeks. It will be announced on Facebook soon. So thank you very much again. Please, if you have some time, fill out our survey. And I wish you a nice evening.
Thank you, Katya.
Thank you. See you. Bye.
Bye-bye.
Bye, Davide. Thank you.
Bye, Martin.
See you.